Okay. So how many of you were able to do the exercise? No, nobody. Great. Okay, so we're going to just review some things. Okay, so we ended up discussing these acid-base equilibria for general acids, general bases. Now, for your amino acids, that's the equilibrium that is analogous to the general acid, general base. And the thing that you want to take advantage of is this concentration. If you know this ratio, then you can tell whether this dominates or this dominates. Right? If this is less than 1, then this is the dominant thing. If this is greater than 1, this is dominating. Okay, so that will allow you to say if it's the charge is 1 plus 1 or neutral or 0. And the same thing goes for the C terminus. So this is and the thing we want to look at is okay, now these two ratios is what goes into this thing here. This is the general acid, this is the general base. So this guy here at the top is NH3+, which is analogous to this guy. NH2 is analogous to that guy. Same thing for these two species. Okay, so now I've told you for lysine, fix the pH. You know all the pKa's, so you can determine if this ratio is less than or greater than 1. So the question now is, so for lysine at pH equals 5 and lysine at pH equals 12, what is the charge? Okay, is it neutral? Is it plus 1? Is it minus 1? Is it plus 2? Okay, so, and of course you need to know what the pKa's are of lysine. So those are in that paper that I passed out. So why don't you try now with this in mind and see if you are able to get it. Yes?
What are we looking for again?
So
want the ratio.
You want, so you actually, well, you have to compute this ratio for these two species in order to answer the question, is lysine neutral or does it have a charge, a net charge, and what is the magnitude of the net charge?
For lysine,
Yeah.
because here we're given for COOH and then we're given for NH3+.
Yeah.
So, like, what will be the remainders here? Like, what will be the neutral state or something like that?
NH3 has plus.
Yeah, it's plus. Oh, okay. So.
Well, it has
okay.
plus.
And minus, so you'll be able to get the short sheet.
Wait. So lysine has, whether it has a plus or minus depends on the pH. So at pH 7, we know that it has a +1. The side chain has a +1. Okay, but so lysine has 3 titratable groups: the C terminus, the COH, the N terminus, and its side chain. So you have to look at, get the charge or the ratio of these two for 2 NH3 groups, because you have the N terminus and the side chain. Okay, so let me sketch it out for you. Let's do the following. So lysine has, that's the R group, and it has an NH question mark. COO question mark. And here I also have an NH question mark. So you need to figure out what these groups are. Okay, I'll give you a hint. You have to start with NH2. And now you have to think about this equilibrium and how this equilibrium changes as a function of pH. So at different pH values, this will have a different protonation state. Okay? So if you want to start by making things simpler, okay, forget about lysine for a second. Consider this equilibrium. Consider this equilibrium and use the pKa values of the N and the C terminus at different pH conditions and see whether you get this one is dominated or this one's dominated. Okay, so first look at this equilibrium and see if you can figure out from this equation, if you can figure out which is the dominant protonation state. Yeah. At which pH? Okay, very good. Now this would mean that if you see lysine, the left, the NH2, that will be like this, right?
Yes.
And also
One with the
even the down. Well, this is where this comes into play. So this is the down one.
Okay.
This is the one above. On the end, yeah. Exactly. So, but you can already see whether you use this value, 10.79 or 8.95, your answer will be
More or less
the same. Exactly. Yeah.
This is supposed to go.
Mm-hmm. Yeah. Remember, you've got a sign missing here. And there's a exactly. So now, this ratio is 10 to the minus.
This dominant.
So exactly. So you know then that the dominant state is the NH3 plus, which you knew more or less anyway. But now you have a quantitative way of knowing this is the case. Right? So and now you'll see that if you went to a pH value.
Because it's acidic, so it's
Exactly.
So that's the
That's where it comes from. Oh, it's the opposite. Yeah. Difference of pH 5, this dominates, pH 12, this one. Perfect. Okay. So now the same for CO, the CO. Okay. On the right track. You don't need your calculator for this. So okay. So this difference is a negative number. So now you know that the ratio of this is 10 to the power of minus 3.95. So that's already telling you that ratio is less than 1. So the concentration of this dominates. So you know that this is already saying to you, by taking 10 to the power, that that's the high concentration speed. So that's the dominant prototype state. And that, you already knew that anyway. When you go to very acidic conditions, it must become prototype. So, is this correct? The total charge at pH 5 is plus 1. Yes, because this is NH3 plus, this is CO minus, this is NH3 plus. So I have plus 1, minus 1. At pH 12, this becomes NH2, this is CO minus, and this is NH2 as well. Okay, so No, so it's -1. -1, yes. -1, okay. Okay. Clear? Now? Okay? So, I think you're mixing, so, okay. Let's start with this one, pH 5. Okay? You get this, you get 10 to the power this, which is less than 1. Okay, so this means that this is higher than this. This is less than this. Okay, so this is telling you that pH 5, you have in lysine, you have NH3 plus on one side, you have NH3 plus on the side chain, and well, you have to work out what's at the right hand side using the same logic. But now it's this. And if you do this thing, you'll see that this dominates. So this contributes. We have a +1, +1, -1. So the total charge is +1 at pH 5. Yeah. No, but this is coming from the calculation. So, because look, this has a charge of -1. This has a charge of 0. So it is coming from the calculation.
Excuse me.
Yeah.
So, is it possible like neutral in one and NH3 plus in one?
Is it possible if, let's say, at pH 9.5,
But for
so if you were at a pH that was in between this pKa and this pKa, so if you, let's say you worked at pH 9.8.
okay, I didn't realize they have different.
Yeah, they have they can have different ones, but for all practical purposes they're the same. Yeah.
So, I did it for all of us, like we're trying to look at the charges of those two.
Yes.
So,
Yes.
for the side chain, it's also NH, it's also
Exactly. Exactly. And
So
depending
it's just
on
which one on the figure itself, like which one, well, both are side chains, like what?
No. So the side chain is the one that sticks out of. So every C alpha group in an amino acid has an R, which is different, and then it has the head and the tail, which is N and C. That's the same for all of amino acids.
I see. So
Independent
that
of
one
the
is the
it's
side chain.
the long thing sticking down is the side chain. Yeah. Okay, so you have it here. So you say when you take this, right, you get -3.95, but 10 to the power of this, right? This is 10 to the power -6.95 is equal to this.
But if you go in zero as in both PS, and you will put zero.
Okay, so this is telling you that this ratio is less than 1.
It is what it is.
So this means that NH3 plus is greater than NH2 concentration. So you know that at this pH, this is the dominant state. It has higher probability. Okay, so for both that N group and the side chain, this contributes +1. So these two groups contribute +2. From this, there's a +1 here and a +1 here. But now if you do the same thing here, the same argument, you'll see that the dominant concentration or dominant state is this. So you have +1, +1, -1. So the total charge is +1.
Or we can also say with the excited displacement. So excited compared to 0 minus 0 COH.
Okay, so please practice this. I promise you, this is one question I will give you in the exam. I give it to you for free, okay? This is one question for free. So, it's a present, exactly. So, you better take advantage of the present. Okay, fine. Now let's think of it. So, if I have a system with a plus charge in the liquid, there's a penalty to pay, right? Because I have to put a plus charge in a dielectric constant of water. I have to pay a solvation energy. So what typically happens in many biological systems, if I have a net charge, there's going to be a counter ion. For example, in this case, I have a +1, so it's very likely that I would have a negative ion, like a chloride ion, to neutralize my object. If I had a -1, it's very likely that I'd have a potassium ion or a sodium ion to create a charge neutral object. Okay, so this is what we're going to get into now. Okay. Okay, so I have these in the notes, so you can look at them yourself. Okay, so let's now shift to Poisson-Boltzmann theory. Where are you? So I just sort of motivated now that at the molecular scale, when I have a charge, often what happens is I have to think about a counter ion that complexes with your charged object. In general, we want to ask, if I have a charged object, for example, like the DNA is negatively charged, how do ions layer or concentrate near the charged surface? What is the distribution of ions? Does it have any special or particular properties? How can we think about it? Now, this is let's say a very standard problem in let's say electrochemistry, which is the following. So I have a charged surface. Okay, let's say I have a negatively charged surface, and I want to know how do the counter ions distribute around the charged surface. So there have been many models, conceptual models, thinking about how to understand how ions layer near charged surfaces. So the simplest one and the most incorrect one is by Helmholtz. So what Helmholtz says is that if I have a charged surface, then all my counter ions layer right near the surface to form something like a capacitor. Okay? It's a very simplistic picture that neglects the solvent, but it's a way to think about how ions would layer near the charge. So in this case, if you would look at the ion distribution, you'd basically have something like a delta function near the surface, and then that's it. Okay? Now, of course, this is probably not so realistic, and so people came up with other models to try and understand how ions would layer near the surface. So this is something known as the Gouy-Chapman model. What the Gouy-Chapman model says is the following. It says that the ions don't specifically bind to the charged surface, but they are distributed around the charged surface through a Boltzmann distribution. A Boltzmann distribution that goes as e to the minus beta v, where v is the electrostatic potential. created by the charged surface. Okay, so this is what we're going to try and look at more carefully. Okay, just for your own education, this is sort of pictures that I've taken from textbooks that show how people think about, if I have a charged surface, how do ions layer near it, and they have these very particular views that the ions near the surface are stuck, they're immobile. So the charged surface polarizes the environment so much that these ions are frozen. They're not mobile. Okay? Okay, so this is for solid liquid interfaces. In solid liquid interfaces, these are not rough, they're not amorphous, they're not soft matter systems. The solid doesn't fluctuate, it doesn't respond to the liquid. For the things that we're interested in, the solute or the charged material is a DNA or a protein. And so, for example, I have a negatively charged DNA, and if I have a negatively charged DNA, well, I'm going to attract counterions. And in the case of DNA, these are magnesium ions typically in the cell. And you want to know, how do the positive ions organize around the charged surface? What is the distribution like? How does the potential look like around the charged surface? Right, so that's the question. And so I would say the most standard way and that people think about this is something known as Poisson-Boltzmann theory. So it comes from the name Poisson-Boltzmann because you combine Poisson's equation and a Boltzmann distribution to study how the ions and the potential distributes. So the question we're asking is, we're taking a very simple geometry now, a flat interface. We're going to look in Cartesian coordinates. You can look at it in polar coordinates too, but for simplicity we're going to look at Cartesian coordinates. And we're going to ask, how does the charge distribution of the counterions look like as you move away from the surface, and how does the potential of what is the potential that the ions feel from the charged surface? Okay, so these are the two questions that we're going to ask. Okay, so it's very, very simple. Gauss's law, derivative of this, and I get Poisson's equation. So I have the potential, which is going to be as a function of moving away from the surface, in terms of the charge density. Okay, what is the charge density? The charge density comes from positive and negative ions. Okay, and I'm assuming that the distribution of the ions as I move away from the surface is characterized by a Boltzmann distribution. It's a Boltzmann distribution in terms of the potential V, where V is essentially the electrostatic potential that's created by the surface. Okay? Z here is the valency of the ion. So if it's sodium, it's +1. If it's magnesium, it's +2. If it's chloride, it's -1. Okay? And E is just the charge of an electron. Okay, so these are the concentrations of how the ions change as I move from the surface to the bulk. So the charge density is the concentration times ZE. Okay, that's the charge density. So if I plug this in now, I have a second order differential equation in terms of the potential V and the charge density. So in principle, I could numerically solve this type of an object. Okay, in principle. But this can often be challenging, depending on the type of system that we're doing. And so we want to start with a simple approximation. in order to solve this analytically. One is, I want to see if I assume something about the magnitude of V versus KBT, I can do a Taylor series expansion. Okay, so if V is small, if this thing here, the exponential is small, I can Taylor series expand it. And if I do that, I get this object here. Okay? This approximation is known as the Debye-Huckel approximation. Okay? And it only holds if the potential V is less than thermal energy. Now we have to think about in the biological systems that we have in mind, in the energy length scales that we talked about, the 4 scales. Is this a fair approximation to make? Okay, but let's say we can make that approximation for now. But I want you to ask the question: is it a fair approximation? Okay, so if I do that, then it's trivial to solve this, and so I can write out the potential as a sum of 2 exponentials. And a quantity that comes out of this, which is the device screening length, lambda d, is related to these prefactors here. So these prefactors involve the dielectric constant of my medium. It involves the temperature that I'm working at, and of course it involves the valence or the charge of the ion and the concentration. So concentration, dielectric constant, and temperature affect the screening length in different ways. Okay, so increasing the dielectric constant increases the screening length. So let's think about that for a second. Increasing the dielectric constant. So if I go from water to something oily, the screening length decreases, which makes sense. So water is a medium that's more polarizable, it's more easy to screen, so the screening length must increase as I increase the dielectric constant. As I increase the concentration of ions, the screening length decreases, which also makes sense, because if I put more counter ions near my charged surface, there's going to be a decrease in the screening. Okay? Okay, so this is a rather, although it comes from a certain approximation, which is that we did this Taylor series expansion, this is a very important quantity because it allows you to calibrate yourself on what the effects of the screening medium are and the concentration on the screening length. And why is that important? Well, that affects the range over which the charged surface will affect counter ions. Okay, this is the, so remember, just like we discussed the Burum length, when I have 2 ions coming close to each other and there's a dielectric screening, and at a certain length that energy, the electrostatic energy, gets much larger than thermal energy. This is very, very analogous to that. But now I have an extended charge interface, I have counter ions, and I have some way of understanding how the screening is affected by the dielectric medium, temperature, and the concentration of ions. Okay, so is this clear? So I just put this here so you can get a sense of the numbers. So as you go from high concentration to low concentration, the device screening length changes by, from about 1 nanometer all the way to 10 nanometers. Okay, so it's significant. So counter ions and how they interact with a charged surface can affect the screening length significantly. Remember, this lambda d goes into this v of x. So within this model, this is an exponential decay. It affects how long the tail of the exponential is. So it can go from 1 nanometer up to 10 nanometers. Okay, so we can explicitly solve for this. So as x goes to infinity, without loss of generality, the potential goes to 0. Okay, so this is 0. The electric field at the surface is given by the surface charge divided by this factor here, which is the dielectric constant times the permittivity. This is the derivative of this. So I now have an expression for A in terms of the device screening length and the surface charge. Okay? So in the Debye-Huckel approximation, i.e. V of x is less than kBt over E, the potential and the charge density both have this exponential dependence. Okay, so this is a first order simple model that one can use to understand how ions layer near a charged surface. And it works quite well. Okay, especially if far away from your interface. By far away, I mean, so let's go to, so right near your interface, there might be some very specific interactions that are not captured by this mean field theory. But as soon as you get away from the specific interaction, so a couple of angstroms, this type of model works reasonably well. Okay? Now, you should keep in mind here that I've written these V of x without assuming I've already taken the average. So this V of x is essentially an integral over z and y. Okay, so it's an average potential. So this is an assumption. Okay. Okay. So, just to go back, if we consider the concentration of potassium ions or sodium ions in the cell, you can show yourself that using a dielectric constant of 80, the device screening length is about 7 angstroms. Well, is that true? I guess it'll depend on case by case. Sometimes it works, sometimes it doesn't. Okay? So, for a surface which had a lot of local charge density with specific interactions of the ions near the surface, this is likely to break down. Okay, if there are not many specific interactions, then this mean field theory works reasonably well. Okay, are there questions on this before I move on? So this is telling you that, if I consider a charged protein, which was produced by these types of charges, then I only really need to worry about correlations between them below 1 nanometer. That's That's what this is saying. Now, if I have two charged proteins that come towards each other, then each of them has a 1 nanometer correlation length. Okay, so then we're talking about 2 nanometers, where I have to start worrying about correlations. Okay. It's too early in the morning, right? Okay, so before is there any question on this before I move on? Let's see. All right. Okay. So I've been talking to you a lot about dielectric constant D equals 80, but we really haven't gone into understanding more about the physics of water and the phase diagram of water, why it's so interesting and special or why we think it's special in the context of biological systems. So, what makes water different from other liquids? Okay, so we've talked a lot about, we mentioned the anomalies of water. Okay, so water has a density maximum at 4 degrees Celsius. Most other liquids do not. Okay. Most liquids, as you decrease or as you increase temperature, density decreases. Okay? Water has a heat capacity minimum in the supercooled region, which most other liquids don't. Water has a compressibility minimum, isothermal compressibility, also in the supercooled region, which other liquids don't. Water also has a very high dielectric constant compared to other liquids. Okay, so let's look at this a bit more and see where this is coming from. So I'm just showing you a bunch of dielectric constants at a fixed temperature for several different liquids, and you see water is separated from the others. Why? Well, because it's related to its polarizability. It's fluctuations in its dipole that are much larger than in other liquids. Okay? Let's look at the heat capacity. Okay, so apart from ammonia, water's heat capacity is very large. And this is a very, very important aspect when you start thinking about dissipation, heat dissipation. So, being the environment in where biological reactions happen, water is a liquid that's able to dissipate heat very efficiently into lots of different vibrational modes. Okay, this is not true for other liquids, well, apart from ammonia. Water has the highest heat of liquid vaporization. So you see at all temperatures, the energy required to take liquid water and convert it into the gas phase is the highest for water compared to other liquids. Why is this relevant? Well, if you were sweating benzene, you would die. Yeah, you would. The amount of heat that would, be released when if you would sweat benzene would be much less. Okay, so sweating water makes you take away more heat from your body when you're heated up. Okay, but this is not true for all liquids. Okay, this is how the density looks as a function of temperature for a standard liquid like ammonia, I think, yes. Most liquids, if you look at the density, it decreases. Methanol, dimethyl ether, but water is special. Water has a density maximum at 4 degrees Celsius. It has a compressibility minimum at 319 Kelvin, and it also has a heat capacity minimum, pretty close to this minimum. Most other liquids, compressibility, if you think about it, the compressibility is a measure of number particle fluctuations or volume fluctuations. If I lower the temperature, you expect those fluctuations to get less. But something weird happens in water. So it is in the normal regime up to some point, and then whoop, it spikes up again. Okay, so this is interesting. Right? Why is what's behind these interesting anomalies? And okay, so this you already know. So those are thermodynamic quantities. And why should we care about looking at the dependence of these anomalies as a function of temperature? Well, I already told you that temperature, for example, and pressure can be a knob to change the stability of a protein. Okay, so these anomalies must couple in some way to changing the stability of proteins on its temperature pressure phase diagram. Okay, so water is also unique because there's this acid-base equilibrium. So it's able to generate protons and hydroxide ions. This is what causes pH. This is what can change electrostatics of biological systems significantly. A lot of biological matter that we've been discussing is built up of nitrogen, hydrogen, and oxygen, which are made up of hydrogen bonds, electrostatic type interactions, dipole-dipole interactions. The same stuff is facilitated by water. Water can form stabilizing dipole-dipole interactions with the peptide backbone. Okay? This is not true for all liquids. Something that is, I'd say, less appreciated in biology is the role of isotopal quantum effects. So this is the density temperature dependence of H2O and D2O. Okay, D2O is the isotope of water. And what do you notice? There's a shift in the peak of the temperature maximum by about 7 degrees Celsius, going from H2O to D2O. That's a huge shift in the position of the density maximum peak. So, thermodynamics, in a classical picture, configurational properties should be independent of the mass. Okay, so if I looked at the free energy difference between liquid H2O and ice H2O, or liquid H2O, liquid D2O and ice D2O, in a classical picture, those should be, they will be exactly the same. Okay, so this is saying something. It's saying something about the role of quantum effects. By quantum effects, I mean things like zero-point energy, so h bar omega. So h bar is playing a role here, and you'll see why. Okay? Just to put this into context, so that's in a liquid. These are experiments where they measure the amount of secondary structure, so alpha helix versus beta sheet. Okay? And they compare it. You have a question? No. Question? No. Someone outside. Okay. If you compare H2O and D2O, the concentration of alpha helix increases. Okay, from 47 to 57%. This is a configurational property. Okay? In a classical picture, these should be exactly the same. So, the alpha helix or the beta sheet is determined by the configuration. It's got nothing to do with momenta in a classical picture. Okay? So, classically, you would expect this to be exactly the same. D2O should not affect the configurational properties, because it's e to the minus beta V times e to the minus kinetic energy. So, something is going on here that's curious and interesting. Okay? Just to reinforce the point again, so this is the temperature at which a protein denatures in light water and heavy water. Again, you see for a series of proteins, there's a big change in the relative difference, free energy between folded and unfolded state. Okay, so what this is telling you is that h bar omega is important. Okay? Now, okay, so this is why it's surprising. There's something changing here, the secondary structure, for example, of your protein, which depends on this. This configurational property is changing, but this configurational property has nothing to do with the mass. It just depends on the potential. So why? Why is it changing? So what is the magnitude of h bar omega in the system? How would you estimate it? So this is 0-point energy, right? Do we all agree that if this is breaking down, I have to worry about this? Because in this classical picture, I'm ignoring this. So okay, so now, what do you think the magnitude of this h bar omega is? Relative to, again, always, kBt. That's always our reference. What types of oscillators? Okay, this is fixed. Where does this come from? What types of frequencies do I need to be thinking about in this, in H2O? How large are the frequencies? smaller, less than, equal?
The system breaks down.
Sorry, sir?
The system
The
breaks.
model breaks down.
Yeah?
You see the system breaks.
No, I'm saying the classical approximation breaks down. Because, you understand why? No. So, I just told you, I just showed you this result. Okay, so you do an experiment, you measure the concentration of percentage of alpha helix, which is a configurational property, in two liquids, H2O and D2O. And you see that there's a difference. If classical statistical mechanics holds, they should be exactly the same. Because the amount of alpha helix depends on this only, where there's no mass dependence. So all I'm saying is that the classical picture is breaking down. So that means I need to think about this. But in order to appreciate this, I need to know how large is it compared to thermal energy in this type of a system. So what types of, say?
Greater than H bar omega is greater than KBT. That's why it breaks down.
That's, yes, it must be. But, so how much is this? So I have, this is the system, essentially. I have frequencies associated with different modes here. Stretch modes, bend modes, rotations. Which frequencies control this? The low or the high? The high frequency. Okay, so the high frequency is vibrations. So if I know what the frequency of a vibration is, I can tell you more or less what H bar omega is. Okay, and so the vibrations of the OH covalent bond are roughly between 3,000 to 4,000 wave numbers. Okay, this is the unit of energy that people use in spectroscopy. Okay? So if you plug this into here, you'll see that it's much larger than KBT. So this 0 point energy is roughly for this is about 0.2 eV. It's huge. 0 point energy is much larger than thermal energy at room temperature. That's 25 milli eV. So, well, you can ask yourself now, what temperature do I need to go to so that these two are on the same order? Say?
1000 Swift.
Exactly. So you remember you learned in your classical stat mech that classical statistical mechanics holds in the limit of high temperature or small mass, or large mass, sorry. And that's a limit, right? But we often assume that at room temperature in a liquid like water, we're in the classical regime. And for some properties, yes, but you see that you would have to go to about 500 to 600 Kelvin before these two are the same order. So at room temperature, 0 point energy is very important for a liquid like water because of this object here. Okay, this is what makes it rather special. Okay. So quantum effects in water are actually very important. Okay, so this is just to reinforce the point. If you look at the frequencies associated with water, there are high frequency modes, vibrations. Then there's bend modes at lower frequency, and then you have this tail here to rotations, and then lower frequency modes. Okay, so this would be like, down here would be the analog of phonons. In the case of water, the vibrons. Okay, down here. But the thing that controls zero point energy is the relevant frequency is this guy here. Okay, so how does this manifest itself in liquid water? How does zero point energy manifest itself? It manifests itself in two things: structural quantities and also momentum quantities. So this is the pair correlation function between O and H. Okay, so I sit on O and I ask, what is the probability of finding an H near me? And overlapped here are experiments, classical models, and then quantum models. Okay, so you got in the Monte Carlo, you guys, well, some of you did the path integral stuff, right? Who did path integrals? No? Nobody? I thought someone did path integrals.
Spin chains, we did spin chains.
Nobody did a quantum. Okay, nobody. Okay, no, fine. Anyway, so this is this guy here. I think it's green. I'm colorblind, so I can't tell. But this one here is what you get from a classical distribution, and this is what you get. The open circles are what you get from experiment. And the solid black line is what you get from a quantum simulation, which you can get from using path integrals. Get Feynman path integrals. And what do you see? What you see here is that the classical simulation significantly over-localizes this OH distribution. So it shrinks it. It makes it look like it's too small. It's only when you look at the quantum fluctuations that you're able to get the broadening of the OH bond. What does this mean physically? What this means is that classically, this proton here has a significant 0 point energy. In the classical world, this is zero. It's not there. However, when you have quantum effects there's some uncertainty. Okay, Heisenberg's uncertainty. The proton has its characteristic thermal de Broglie wavelength, and that de Broglie wavelength gives it some uncertainty, and so there's a spread here of distances, and so this tends to be more delocalized, and that's why you see that. It's a very subtle effect. Okay, so we're talking about 0.1, 0.2 angstroms. You may think it's a very small number, but very small changes in those types of length scales can affect electronic structure in highly non-trivial ways. Okay? So that's one effect of how it's manifested. The other one is in the momentum. So in the classical world, the momentum distribution is Maxwell-Boltzmann distribution. That's this guy. If you look at the proton momentum distribution from the quantum simulation, they are shifted, they're different. They're the classical Maxwell-Boltzmann distribution. Okay, so quantum effects in liquid water are very, very, very important. They manifest themselves in both structural and kinetic energy. So in both position and momentum, in highly non-trivial ways. And these are the types of things that one can also measure experimentally. Okay, so the reason why people are interested in this from theory is that there are experiments that you can compare with and you can validate your models. Okay, questions? Okay, I think we'll stop for today. And then we'll continue on Tuesday. Are there any questions from?
There's one.
Yeah, please.
I saw somewhere you call water a universal solvent. Does
A?
everything a universal solvent?
Yes?
Does everything that dissolves in? Okay, what do you mean?
Most things. Okay, many things.
Dissolve?
Yes, dissolve in water. Many things. Okay, of course, oil doesn't dissolve in water, but many biological things are happy in water because of favorable solvation. Okay, no questions, so we'll continue on Tuesday. So for homework, actually, I want you to do the following. Tell me what the thermal de Broglie wavelength is for oxygen and hydrogen. And then I want you to think about how that length compares with the length of a hydrogen bond. William, you know where to go, right?
Not really. I'm just going to check it out.
Okay. It's in the have you been to the old CISA building before?
Yep.
Yeah, that's right, there. And
Yes,
it's
yes,
the
yes.
top floor.
Okay.
Okay.